Use table 1 to find the Maclaurin series for f of x equals e to the 3x minus e to the 2x. Referring to table 1, we see that e to the x has the expression sigma as n goes to infinity of x to the n over n factorial and a radius that is infinite. So f of x here is going to equal the sum as n goes from 0 to infinity of x cubed to the n over n factorial minus the sum as n goes from 0 to infinity of x squared to the n over n factorial. Combining these into a single summation expression here, we have the sum as n goes from 0 to infinity of x to the 3n minus x to the 2n over n factorial. And since each of the original expressions had an infinite radius, the radius will still be infinity because adding together two series won't change that. Next, we have the same instructions, and our new function is f of x is equal to x squared times the natural log of 1 plus x cubed. Again, referring to table 1, we see that the natural log of 1 plus x is equal to the sum as n goes from 1 to infinity of negative 1 to the n minus 1 times x to the n over n, and a radius of r equals 1. So our function f of x is going to equal x squared times the sum as n goes from 1 to infinity of negative 1 to the n minus 1 times x cubed to the n over n. Simplifying gives us the sum as n goes from 1 to infinity of negative 1 to the n minus 1 x to the 3n plus 2 over n. The 3n, of course, comes from x cubed to the n, and then the exponent of 2 on the outside factor then just gets combined as an expression with a common base. Again, nothing we did changed is the radius. You could verify this using the ratio test, and the radius is 1. Next, we're asked to use series to evaluate a limit, and here it's the limit as x approaches 0 of 1 minus the cosine of x over 1 plus x minus e to the x. A quick check here, if we were to let x equal 0 and try to substitute, we would end up with an indeterminate form, so that's not going to help us. We could use L'Hopital's rule, but here we're looking at using series. Again, looking at table 1, we have the cosine of x is equal to the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial, and e to the x was as it was given a few minutes ago. It won't be very useful for us to use the sigma notation, so we're going to expand this when we write out the limit. So what I'd like you to do is pause the video here and replace the cosine of x and e to the x using, say, 3 to 4 terms. Replacing gives me in the limit as x approaches 0 in the numerator 1 minus 1, the quantity of 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial and so on. In the denominator 1 plus x minus, and then the expression that we have for e to the x, 1 plus x squared over 2 plus x cubed over 3 factorial, and so on. We see that some things will subtract out. 1 minus 1 subtracts out in the numerator, and in the denominator, 1 minus 1 and x minus x both subtract out. What we are left with, after distributing the negative in both the numerator and denominator, is the limit as x approaches 0 of x squared over 2 minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial and so on, over negative x squared over 2 minus x cubed over 3 and so on. Now what I'd like to do, if this was as x approaches infinity, then I would divide by the largest power that appears in the denominator. I would divide that out of the numerator and denominator. That would be problematic here because we don't have a largest power in the denominator. This is an infinite series. Here, though, we're asked to find the limit as x approaches 0. My tactic there is to divide out the smallest power that appears in the denominator. And the reason I want to do that is because if I divide out the smallest power of x in the denominator, then I'll be left with at least one non-zero term in the denominator, and that's what I'm going for. Let's see what that looks like. Dividing numerator and denominator by x squared gives me a leading term in the numerator of 1/2, and then minus x squared over 4 factorial plus x to the 4th over 6 factorial, a bunch of terms that all contain x. In the denominator, I have negative 1/2 minus x over 3 and a bunch of terms that all contain x. All of these terms that contain x, as x goes to 0, will be 0. This leaves us with an answer of negative 1. Next, we're going to see a slightly different view of table 1. We were asked to find the sum of the series. The sum is n goes from 1 to infinity of negative 1 to the n over pi to the 2n all over 6 to the 2n times 2n factorial. What we want to do is look at table 1 and see if we can match anything up. Looking at table 1, I can see that we have x to the 2n over 2n factorial as a description for the cosine of x. Of course, there's the negative 1 to the n, which means that it's alternating. The series that we are given has that alternating negative 1 to the n. 2n factorial is really what gives it away for me. And looking at this, we can see that we have pi to the 2n and 6 to the 2n, one in the numerator, one in the denominator. That's the same thing as pi over 6 to the 2n. And so comparing what we see here, we see that x is equal to pi over 6. In other words, the sum of this series is going to be the cosine of pi over 6, which is the square root of 3 over 2.